Okay, hello everyone. So today we're going to continue our discussion and finally get into the real main idea behind the support vector stuff that this unit is about. So we have this very important picture here, which tells us a number of things about the geometry of the decision region in linear classification. So one thing we learned last time is that if the decision boundary is, let's say here, that the W vector, the vector of the weights, not including the intercept, is orthogonal to it. We also saw that if you know the decision boundary, you can get a lot of information about the weights and the intercept just by looking at the W's and the B, by looking at where the boundary intersects the coordinate axes. And we also use these ideas to derive a signed distance from any one of these training points to the boundary. And that signed distance is what we're going to be using today. So sort of intuitively, the farther a point is from the decision boundary, the easier it is to classify. The ones that are close to the decision boundary, those are the ones that are more difficult to classify because they're the points where there's less separation between the two classes. So, so it's useful to know exactly how far any given point is from the decision boundary. We went through a derivation to get this expression here. And one important thing about this is that this is what we call a signed distance, in that unlike usual distances which are non-negative, this distance could be positive or negative. And when we're on one side of the boundary and you're saying how far do I have to move towards the boundary in this direction, that will have the opposite sign on the distance as when you're on this side and you're moving in this direction to the boundary. So that's an important thing about this this signed distance. And then one last thing we recognize is that if you scale both the B and the W together, it does not change where the boundary lies. Because you can see that if I scale both of them by alpha, that alpha would basically cancel here and it would not move the boundary at all. So we think of all positive scalings of the B and W together as equivalent. They all give the same decision boundary at the end of the day. One thing that they do change, however, is they change the value. As you change alpha, you change the value of the score Z for a given point X, right? The larger that alpha gets, the larger the magnitude that Z would get. Okay, so in terms of Z, yes, scaling B and W change that, but in terms of actually where this boundary is, scaling B and W together don't change that at all. Okay, so these are all the concepts we have from last time. Are there any questions on this? These are all pretty important. Okay, so now let's come back to the notion of linearly separable, which I think we talked about once before, although briefly. And the idea is if you have a training data set, let's say I have these square points here and circle points here. If I can pass a linear boundary between them so that on one side of the boundary you have all of the points from one class and on the other side you have all the points from the other class, we say that this data set is linearly separable. And if we have a linearly separable data set, that's great for linear classification because we know we could perfectly classify our our training data without any errors. It doesn't usually happen in practice, but still it's an important idea, and it is sort of the thing we start with to design these support vector classifiers. So now let's be a little bit more precise to come up with a mathematical definition, a way we can write this down with math. So to do this, we're going to assume, to make the math cleaner, we're going to assume that the labels are plus minus 1 versus 0 and 1. And we are going to start out by saying that this data set is linearly separable if there exists some B and W, and remember the B and W together give you that, right? So some B and W and some small positive number epsilon such that, such that whenever y equals 1, we get that zi, which we can also write as bi plus xi transpose w, is greater or equal to epsilon. On the other hand, if yi equals minus 1, then the zi's, which of course have the same form, is going to be less than or equal to negative epsilon. Okay, so let's think what that means. So remember that Zi is the score for the ith training sample. That is the quantity that we use to make a decision if we had to make a decision about that sample. And whenever Zi is positive, we decide that yi is 1. Whenever Zi is negative, we decide that yi is minus 1. And here you can see that's all represented in these equations, right? Because epsilon is a positive number, so we're saying Zi is greater than or equal to some, maybe very small positive number, whenever y equals 1. So that's just sort of reflecting this idea we have about how the sign of Zi tells us the class. Okay, so that's going to be where we start with. Is everybody okay with that definition? Does that part make sense? Okay, so we'd like to simplify this. So notice that, okay, I have two inequalities. That's not so convenient. But I can actually rewrite them as a single inequality if I multiply the left side by yi. Because in the first case, I multiply by 1, nothing changes. But in the second case, when I multiply by minus 1, we know that that will change the sign of the inequality and will also kill this sign. So if I now consider this statement, this is equivalent, but I have a single inequality rather than two. So this is just saying the same thing, but in a cleaner way. Okay, so you could say that this is, again, the score on sample I, and this is like a sign correction of that score. So we want, whenever the score is positive, we keep it positive, but if the score is negative, and that's for this sample y equals negative 1, we just negate that negative score, and then we expect that to be positive. So this is our new improved statement of linear separability. Okay. Is that part, is everybody okay with that? Okay. Now, we want to make this even simpler because right now what's inconvenient is that we have this parameter epsilon. We don't really want to have to decide on a particular parameter epsilon. There's nothing really special about that epsilon. It's just that there exists, we're looking for some epsilon. But what if I divide both sides of this inequality by epsilon? So we know it's positive, so it doesn't change the sign, in which case I'll get beta over epsilon, w over epsilon, and a 1. So now it's like I have an inequality stated with a scaled classifier. Right? This classifier is scaled by 1 over epsilon, which is similar to the alpha on the previous page. And we said actually these classifiers are equivalent. That scaling does not change where this line, where the boundary actually sits. So essentially, it's enough to just consider epsilon equals 1. So in 2 steps, what we do is we divide both sides of this by epsilon. Then we realize that the new classifier is equivalent to the old one, so we just go back to the old one instead of using this new one. And then we get this further simplified statement of linear separability. And this is the one we want to use from now on. So this backwards E is there exists. So there exists some combination of B and W such that for all samples I, this sign-corrected score is greater or equal to 1. Okay. And, you know, this doesn't necessarily hold for all B and W. Even if the boundary is in the correct place, B and W might not be scaled properly to have this true for all samples. But that's okay because we can just scale them simultaneously, and eventually we'll find a pair where the boundary is the same, but this is true for all samples. So that's where we finally land with linear separability. So this is our main definition here. Okay, so that's what we're going to use going forward. But we can make one last observation. Notice that this quantity here, we can see that reflected here. And in fact, by moving W over to the other side of this, I could rewrite this as norm of W times gamma I. So let's do that. Let's rewrite this as, I'll write it gamma I times norm of W. And then in one final step, I will divide both sides of this inequality by norm of W, and we finally get this statement. And this statement here is very important. So remember what gamma I is. This is the signed distance from point xi to the boundary. It's the signed distance. This is correcting the sign on that signed distance to make it positive. So now we're saying the sign corrected distance, I'll write that down. This thing is a sign corrected distance from the ith point to the boundary should be greater or equal to this number, 1 over the norm of W, for all the samples I. And this number is very important, so we actually give it a name of, or a notation of gamma, and we call it the margin. So in this picture here, this hopefully helps to explain things. So for the points on this side, we have these signed distances like this. For the points on this side, we have signed distances that have the opposite sign. But if we multiply them by yi, they all have the same sign. They're all positive, and we can really think of them as distances. And then this says those positive distances are all greater or equal to some number. So that number, the margin, is basically the gap, the minimum gap between the boundary and all points in the data set. Okay, so this is what we can do if we have linearly separable data. We know that this holds. This comes directly from this definition. So what do we want about gamma? Do we care about the size of gamma? What do you guys think?
We want it to be large so we're confident.
Want it to be large, yeah. So like for example, this is a boundary that also gives linear separability. But for that boundary, we would have a very small gamma because the distance, we found a point, that has that distance. So from a practical standpoint, what don't we like about this boundary?
We
yeah.
evenly spaced in
Why,
between, not-
why, but why?
'cause
I mean-
we're assuming that when we get more data, we want it to fall on either side of the line, and we're kind of pushing
Mhm.
up against.
Exactly. We're thinking about what's going to happen when we see test data. For the training data, any linearly separable boundary is equally good. But once I see test data, it's not going to be, exactly in the same places as my training data. I'm thinking, let's say based on this picture, that the test data should be roughly over here and over here. But, there could be some test data points maybe just over here. And if there is, and I put my boundary there, I'm going to be making a mistake. But if I put my boundary here, this is the most robust place I can put it because it has the biggest gap where I can possibly still get test points that are slightly different than my training but not make an error. So really, this is the most robust choice among all possible boundaries. This one looks to be the most robust. It has the largest minimum distance from the boundary to all the points. Okay, so that's what we like about this idea. And the margin, is sort of clearly describing this concept. This is the worst case distance between the training set and the boundary. We want that to be as large as possible. Sometimes people call this thing the street. It looks kind of like a street, right? You want to keep your training points outside of the street. Also, you want your street to be as wide as possible. If I make a boundary here and I define my street as that which doesn't contain any training points, I have a pretty narrow street. There's not a lot of room for error. So I want to try to find a boundary where the street is as wide as possible. So that's the whole idea behind the units, the methods in this unit. Okay, so we have the margin, which is, you could say, the half width of the street. It's defined this way. It's, when you look at the sign corrected distances, it is it's a lower bound on all of them. Okay, so those are the main ideas. Any questions about this? 'Cause these are somewhat tricky concepts, but they're kind of the heart of what we're doing in this unit. Okay, does it seem clear? Or if one of you guys have a question, someone else probably has the same question, so don't be afraid to ask it. Okay, everybody's good? All right. So as we just described, if our goal is to make the classifier robust, what we want to do is we want to maximize that margin. We want to find a street whose width is the largest. And if you look back at these equations, if I want to maximize gamma, then I want to minimize the norm of W, right? Minimizing this will maximize its inverse, which is the margin. Of course, that only makes sense if I'm making a linearly separable classifier. If I start to put my classifier over here, that no longer makes any sense whatsoever. So we need this to happen for all I, so we need linear separability. But now, in addition to that, we want to minimize the norm of W. Okay, so that gives us a concrete way to design our method. So in particular, we can set up an optimization problem now where we do minimize over B and our W vector. One half of the norm of W squared. But importantly, we need to add the constraint, the linear separability constraint, such that yi times B plus xi transpose W is greater or equal to 1 for all I equals 1 dot n, 1 to n. Okay, so now we've turned this idea into an optimization problem. It turns out that this is a convex optimization problem, so it can be solved. We can solve it. It is a constrained optimization problem, as you can see, because we want to minimize this subject to some inequality constraints. But we know that those things, we know there's ways to handle that. A couple other things to note. We're putting in a 1/2 here. That doesn't really affect anything. We could just as easily leave that out. But it's typically added just because sometimes, you know, when you think about like maybe taking a gradient of this, the 2 will come down and we'll cancel this, and the resulting expression will be a little neater. So it's common whenever you see squared norms like this to have a 1/2 to absorb that 2 in the gradient, but it's just a convention. And then similarly, we have a square here. We don't necessarily need a square. We could do without that square, but it turns out that when you have the square there, all the math becomes a lot easier with that squared 2 norm than without the square. So that there is another optional thing, but it is usually used just to make the math easier. Okay, so design our linear classifier to minimize this, to maximize the margin, to minimize the norm of W, while keeping the data linearly separable. So while keeping the boundary linearly separating all of our training data. Okay, so another way to paraphrase what we're doing is we're finding the B and W so that out of all of them that give you linear separability, this is going to be the one yielding the widest street. It's the one with the smallest W norm. So here again, we just have another picture where we have found that. Any questions on this so-called hard margin classifier? Yes.
I have a question about the street. So on both sides of the street, do you assume that those lanes are like the same width, or like once you find
Yeah.
out, you go to both sides?
They're the same width because, yeah, the gamma is the half width of the street. So we're not really treating one class any differently than the other. Yeah. Okay, so is everybody good with this hard margin classifier? Okay, so this is going to do exactly what we want. If you solve this optimization problem on this data set, it will find this most robust line. And what's interesting is you can sort of see this graphically that it's only going to depend on those 3 training points, right? Because if I move this other point, either a little bit farther away or a little bit closer, it does not change this worst case distance, the smallest distance from the training set to the boundary, right? It just doesn't change that at all. The only points that matter to determine that boundary are these 3. So this gets back when we motivated this, I think it was on Friday. We said we're looking for techniques, a classification technique that is going to focus on a few most important training samples and not get distracted by the easy ones. It's going to focus on the hard ones. And that's exactly what's being done here. These are the hardest training samples to classify. This design is focusing entirely on those. And it is basically ignoring the details of all those other training values. So this is one of these techniques. So the design is determined by the few training X that are nearest to the boundary, and we give these the name support vectors. Those 3 points are the support vectors. Okay, so we see this graphically. We'll come back and we'll sort of prove that, yes, there's a finite number of points that determine the design. But for now, you can see it at least graphically. Okay, so how are we doing on this? Any questions? Is it sort of making sense? Okay. All right, so there is one big problem with this technique. And the big problem is that for the way we're stating it here, you need your training data to be linearly separable to even solve this optimization problem. So if you happen to have a training data set where, let's say, there's a black point over here, there's no way to get a linear boundary that linearly separates the data, and you basically can't use this. It just doesn't say what to do because it's impossible to satisfy that constraint. Okay, so the next step is to change things a little bit, to relax things a little bit so that it's going to do what we want. It's going to do exactly this when the data is linearly separable, but when the data is not linearly separable, it's still going to do something smart, something that is, in the end, exactly what we want it to do. So that's the next step. Any last questions before we move on? Okay. All right, so this is now what we do to handle data that is, I'll say maybe not linearly separable. It could be, but generally speaking, in practice, it's not going to be. What we do is we take our linear separability constraint. So I'll just remind you what that is. The way we have been writing it, it's yi times b plus xi transpose w greater or equal to 1 for all I. So that's how we started writing it. Let's just rewrite this a little bit different by bringing the left side to the right side. So I'm going to subtract the yi term from both sides. So the left will be 0, and the right will be 1 minus yi times a quantity b plus xi times w, that whole thing, for all I. Okay, so this is a constraint on the ith training sample, but we want this to hold for all I. And hopefully you can see that these are equivalent. All I'm doing is just bringing that to the other side and rewriting it. Once we have it in this form, you can see, okay, I have this term here. I want this term to be, I never want this term to be positive. Right? I never want it to be positive. So what we're going to do is, instead of having a hard constraint, as we did here, constrained optimization problem, we're going to replace that with a cost term, a second cost term with this form. So this is the sum of the max of two real numbers. It's the max of 0 and this term. So for example, if this term was greater than 0, this max would return this term. On the other hand, if this term was less than 0, the max would return 0, because that's greater than this when this is negative. Right? So I'm just trying to explain what this is doing. So notice that, okay, if we really do have linearly separable data, that means this term is 0 or less for all I, in which case, if this is 0 or less for all I, the max of that and 0 will be 0, and you'll sum up zeros, and you will actually get this equal to 0 if the data is linearly separable. Okay, so it is possible to drive this cost all the way to 0 for linearly separable data, and that's the lowest value you can get. However, if there is absolutely no way to find a BW combination to satisfy this for all I, then that's okay. You can still drive this down to some minimum value, but that minimum value will be positive. But there's still, a smallest value you can get down to. So what we're going to do then is just replace this constraint by plus that new term. And we will now have an unconstrained optimization problem. So here's the new term plus the old term. And there's one last detail, is let's put in an adjustable weight here, tunable weight, that will help us balance these two terms. Because it is really important to balance them. We're really asking the design to do kind of two separate things, but two interconnected things. Okay, so let me first pause and say, is it clear how I got from this design, the hard margin classifier, to this design? Any questions on that? It's replacing this constraint with this cost. So now I have a sum of two things, unconstrained. Okay, this new design is called, it's a soft margin classifier, or we'll call it the support vector classifier. Okay, so C is going to trade off, when we do this minimization, we want to minimize the sum. So if I choose C really large, that means that it's going to be very sensitive to this. So if C is large, when you do the minimization, it will do whatever it can not to make this very large. It will allow this to be large just so that this part doesn't get multiplied by some huge value for C. Okay, so large C means it encourages this to be small and doesn't care as much about that. On the other hand, if C is small, then it allows this to be very large, and it will encourage this to be small. So C just sort of trades off between those two. And the first term basically is summing up how many places have you violated this linear separability constraint. Because when the constraint is not violated, we know we get zeros. This whole thing is zero. But if C is small, we're going to basically be saying it's okay to make some errors in terms of linear separability. In terms of the picture, that means that some of these points will be inside the street or possibly even on the wrong side of the street. That's what happens whenever this is violated. When this holds, it means that all the points are on the good side of the street. Okay. So by making C small, we allow some points to be in the street or on the wrong side of the street. Meanwhile, if C is small, we're allowing W to be big. And when W is big, the margin, so when large W gives a small margin or a small street width. So let me show you in terms of a picture. So this picture shows designs for three values of C: large C, medium, and small. Okay, so when C is large, what this says is we really don't want to make any mistakes in terms of linear separability. However, we allow this to be large, which means we're making our street narrow. And the support vectors are circled in red. You can see that there's relatively few support vectors. From the support vectors, you can infer where the street is. So the street is, it's hard to draw, but it's quite a narrow street. Something like this. On the other hand, once I decrease C, now I'm saying it's okay to make mistakes. It's okay to have samples in the street on the wrong side of the street. Simultaneously, it's okay for the street to be wider. And so now we have a wider street, we have more support vectors. If you decrease C by another couple orders of magnitude, now the street is extremely wide. There's only a few points left that are not in the street. So in this latter case, you are basically saying it's fine for this to be large because we'll make it small with C, but this thing, we really want to make this small. That small means a wide street. Okay, so this is the role of C, is you're going to trade off between how many of your training samples are you using to determine that boundary. Do you want to just use a few that are the very few hardest ones, or do you want to involve a lot of them? There still will be some that you're not using at all, but all these other ones are going to be involved in determining that boundary. So that's the role of C in this problem. So it's a really important tuning parameter. Okay, so all right, any questions on that last part? Yes.
Yeah, so in the pictures of the next slide,
Yeah.
if there was some red point that was like way outside over with the blues,
Uh-huh.
we're assuming that it could be over there given the rest of the data.
Yeah.
If it was outside of the street, would it no longer be a support vector? Even if it's like outside on the wrong side of blue?
So it's a support vector whenever it's in the street or on the wrong side.
Okay.
Yeah. So the only way it's not a support vector if it's on the correct side of the street. Yeah, so you can actually see that with some data sets, like let's say that there's a bunch of red points over here or a bunch of blue points over here. There's no way to make any linear classifier where those are not going to be support vectors because they're just simply on the wrong side of any boundary you construct. So there's going to be a minimum number of support vectors. If your data is linearly separable, you can choose C small enough so that there's only that minimum number of support vectors. That is possible. And in fact, that leads us to this idea. So if you do have linearly separable data and you make C large enough, you will find that this new idea, the soft margin classifier, gives you exactly the same design as a hard margin classifier over here that we originally proposed. So we can completely cover this. This is a pure generalization that allows us to do that, but even be more flexible and handle data that is just not linearly separable. Okay, so this is a really nice design. It's going to give us a decision boundary that should be more robust than logistic regression. And we'll see it is the case. It does work a bit better. Okay, so all right, so that's support vector classifier. Is everybody okay with this, or are there any questions on this? Okay, so let's keep thinking about the effect of this penalty C from a different perspective. So on the left, you can see that I have a situation where I am using just a few training data points to do my design. On the right, I'm using many training data points. So we can interpret this in terms of a bias variance trade-off. As we know, when we use just a few training points, if you imagine doing many random experiments where you have random draws of that training data set, you're going to get fluctuations from one experiment to the next, from one draw to the next, right? Because every time you're drawing a different set of random points, and so, for example, if we generate the blue and red points randomly, you would notice every time we do this, the line is going to be changing its location slightly, right? Because those few points that determine the line are changing. And since there's only, I don't know, maybe 8 of them or 7 of them or whatever, they're going to be changing, a non-trivial amount every time we do this. On the other hand, over here, you can see that this line is really, in some sense, the average of all those points. All those points have some effect, so as I move one given point, it doesn't really change the line very much at all. So if I did this experiment over and over again with random points, I would see that this line doesn't really fluctuate very much. Okay, so in terms of variance, this is going to be a high variance solution. This is going to be a low variance solution. So here we've talked about, so let's say larger C means smaller margin, smaller street, higher variance. That's the left side. Smaller C, right side, lower variance. Okay. Is everybody okay with that idea? Okay. What about the bias? So let's take a close look at what's happening here. So how many points are we misclassifying here in terms of The blue, I don't know, maybe this point is getting misclassified. I think it's on the wrong side of the boundary. Looks like all the red points are on the correct side, so maybe we're misclassifying one. But look what's happening over here. All these blue points here are being misclassified. All these red points are being misclassified. So now there's something structurally off with this line. It is just simply rotated clockwise in kind of a bad way. That is causing bias. That is causing a systematic error for this boundary where you're going to be making a bunch of decision errors on the training data set over and over again. Every time you draw this new random set of points, the line won't change much. Yes, the points will be in different locations, but you will be consistently making errors on a bunch more than you're doing over here. Okay? So over here on the right, we have high bias. On the left, we have low bias. So this is another way we can think of this role of C. It's a bias variance trade-off. Where we exactly want to be on the bias variance trade-off really depends on how much data we have, on the details of our design. We can solve this problem like we always do with cross-validation, make a grid of C's, do cross-validation, like leave one out cross-validation, whatever we want, and we can try all the different C's and pick the one that minimizes our cross-validation error. So we know how to handle that. So this is a very useful interpretation. Okay, so that's another interpretation of C. Any questions on that? Is that making sense? Okay. And I kind of mentioned this already, but I'll mention it again. So generally speaking, we're saying as you increase C, you get fewer support vectors, but there's a limit. Eventually, you can take C to infinity, but there's no way with a linear boundary, if you have points on the wrong side of a linear boundary, there's no way you can ever correctly classify them, and so you always have them be support vectors. There's a minimum number of support vectors. So there's a minimum number. As you decrease C down from infinity, you will start to see more and more support vectors from that minimum number. Eventually, all your data will be used, they will all be support vectors. In the other direction, there's a minimum number. Like in this data set, this one looks like the minimum number is going to be 3. But some other data sets could have a lot more than 3. Okay, so those are, I think that's the main idea behind choosing C in this design. Okay, any questions on that? Great. Now let's relate it to things we've seen before. So let's take this C over here. Since I'm doing this minimization problem, I can scale the entire cost function by a scalar, and that won't change the minimum values of B and W. So let me scale this entire thing by 1 over C, which basically puts the C over here. So it moves it over there. So that is actually very similar to something we've seen before. For example, this is what we saw with L2 regularized logistic regression. Here's that term that we derived in class that minimizes the cross entropy term. And then here's our ridge regression penalty, L2 regression. And when we first did it, we had an alpha here, but we noticed that when scikit-learn implements things, instead of doing alpha, they have like an inverse alpha, which they in fact call it C. That's like something in the denominator. Okay, so this is exactly how scikit-learn implements logistic regression. Basically the only way to make this 0 would be to take C to infinity, and you can never do that. So it forces you to always have some penalty there, even if it's tiny. So we've done essentially the same thing. You can say, okay, look, we also have some loss. It's a little bit different than this, plus a ridge term. So, okay, then the question is, well, how does this loss differ from this? Can we make a plot to understand this? So here's a plot. I'm going to focus on the case where yi is 1 in both designs, so assume a positive label. If yi is -1, the plot just flips from left to right. It looks the same otherwise, so let's just focus on when yi equals 1, in which case this is a nice simple shape. It comes down with a slope of 1 until the value 1, and then it just moves to the right with slope of 0 and value 0. This thing is called the hinge loss. Now you might ask, well, okay, I understand that. Well, how does this loss look like? Well, that is, logistic one looks like this. So they're very, very similar. They both, if you go far over here, they both have a slope of 1. If you go far to this side, they're both very close to 0. But the difference is that with this SVC, the hinge loss goes exactly to 0 at some point. Logistic loss shrinks but never quite goes to 0. So what that means is, in this hinge loss, any samples xi which give me a zi greater than 1 are not involved at all in the cost function. We're throwing them out. Whereas logistic keeps all the samples, even samples that are very far away, very easy to classify, it is still using those. And that might be the reason when we saw the pictures of MNIST and we saw that as we increase the number of samples in our training data set, we saw the logistic regression was using all of them, and maybe it was starting to do some weird stuff where it was getting distracted by the easy samples and not focusing on the hard ones. Okay, so SVC is going to focus on the hard ones, and you can see that directly in this loss here, this hinge loss. So any samples, this is the boundary of the street. This is when you're in the street, and this is the boundary, classifier boundary, zi equals 0. To the left of this, to the left of 0, you're on the wrong side of the street. You're making a classification error. Here, you're in the street. You're not making a classification error, but the SVC is complaining. It doesn't want you to be in the street. Okay, so here again, we see this notion of support vectors. And the logistic loss penalizes all samples. SVC only penalizes the support vectors. Okay, any questions about this? Okay, great. Now, if you look at the Wikipedia page, I'm pretty sure that that's where this link is going. You'll see the SVC written in a way that you might not recognize. So I want to just have a slide in interpreting it. There's another way to write it, using something called slack variables. It's really a pretty minor change from how we wrote it before. So this is how we wrote the SVC. So we have these terms here, which is the max of 0 and this 1 minus yizi. So this other way of writing the C just takes that max quantity and just gives it a name. In this case, it's xi. And then so it just writes that sum over the xi. So here's the sum. Okay, we're going to bring the C over here instead of putting it there. It's just a minor change. But here you see the sum of the xi's, and here you see the L2 term. Okay, and so that's what it does. Okay, but in doing that, we lost all the important structure that we saw about the term. So now we have to add back in that structure. And in this case, they do it by adding some constraints on the xi's. The constraints make sense when you look at this. You can see that xi is the max of either 0 or this term, which means it can never be smaller than both of them, right? It has to be larger than 0 and larger than this in all cases. So it does that by adding two constraints. One is a constraint greater than or equals 0. The other is a constraint on this other thing, 1 minus yizi. Okay, so it's just rewriting the problem in a slightly different form using these slack variables. And the slack variables can be visualized too. They are the distances between these points and the street, basically. So if you have xi I equals 0, that means that that sample I is outside the street on the good side. So all these blue points would have xi I equals 0. Now, if you're in the street, somewhere over here, you have a xi I. So it's 0, it grows to 1, then it grows to 2, then it keeps growing to 3, 4, and so on. So it depends how far you go. So 0 to 2 would be in the street. And if xi I is 1 or larger, you're on the wrong side of the street. Misclassified. Okay, so the xi I's are very interpretable. This guy here. If we're talking about the red ones, we have to change direction. So now for the red ones, these are on the correct side of the street. They have xi I equals 0. Once you're in the street, you have xi I growing from 0 to 1 to 2 to 3 and so on as you go further. Okay, and any xi I greater than 0 would be a violation of the margin. You're not on the good side of the street. So just a different way to write it in case you see it somewhere else written like this. Okay, any questions on this? Okay. Oh, yes.
What is that center arrow showing?
This one?
Yeah.
Let's see.
Is that just the direction from that line where the red points would have a?
Yeah, it's a good question.
Isn't that W?
It could be W. Yeah. We'll label it as W. Okay. All right. Any other questions? Okay. One last topic for today is, what if we have more than 2 classes? Can we extend this idea? So we know how to do it with linear regression in general. What we do is, instead of having a single W vector, with this one versus rest approach, we train a separate vector for every class little k. Basically, this would say it's in class 1 or not in class 1. Next is in class 2 or not in class 2, and so on. So now we have a separate intercept and weight vector for every class. That means we get a separate score scalar for every class, and we can concatenate them together in a vector of scores. And this is all for the ith training sample here. Okay, so the question now is, how do we train the B's and the W's? So one approach, the simple approach, is to say, let me first train B1 and W1 in isolation, forgetting about all the other B's and W's. And to do that, I'll take my training data set, I'll take out class 1, and then I'll take all the other classes and make a temporary second class, and I'll do a binary classifier with the SVC we just learned about, and I'll design my B1 and W1 that way. Then I'll come back to my data, I'll take out class 2, and take out, put that on the other side of all the other classes, and I'll design B2 and W2, and so on. And eventually I'll have designs for all these. So that would be the separate training of one versus rest binary SVCs. But there is another option, which is to jointly train them. We saw something similar in logistic regression. We called it multinomial logistic regression. It was a more complicated procedure that trained all the B's and W's together. And there is a version for the SVC called the Kramer-Singer approach. And when you look at it, it looks a little complicated. So now we have the same sum over I, but now we have a sum over label indices j not equal to yi. And we have a hinge-like thing, but there's actually like 2 different versions of z in there and so on. This part looks the same. We have the Frobenius norm in the matrix, which is just this is the square. This is basically like the sum of the squares of all the W coefficient. So that part's the same. Even though this looks different, you can, I don't think I'm going to go through this right now, but you can kind of go through and you can convince yourself that in the special case that you do have, let's say, exactly 2 classes, if you use this, you will eventually recover exactly the same SVC as we have over here. It reduces to the same thing. So it really is just a direct generalization of what we had to multiple classes. And what you find in practice, when you run this, it is more computationally expensive, but it tends to work a little bit better. Same as we saw with the MLR, more expensive, but tends to work a little bit better. Okay, so the very last thing is, if we're doing this in sklearn, it's not surprising, given everything we've seen before. So this is going to be called it's in the SVM library. It's called the linear SVC. And there's a few interesting things about the options or the defaults. Okay, so not surprisingly, you give it the C parameter. We saw today larger C means fewer support vectors, but only up to a point. There's a minimum number. What's interesting is that by default, it does not use the hinge loss over here. It uses the squared hinge loss, so it puts the square in there. Okay. So why, anybody have a guess why we might want to use a square there? What could be advantageous about that?
Would that be penalizing, I guess, the reason why it'd be penalizing more for something really far away, or if it's like really far away on the other?
So it's more of a computational thing. So here's the blue curve, right? So imagine that if I put a square there, I'm just squaring this, I get a parabola. Okay. Notice that it's smooth. It's differentiable everywhere. I didn't draw it well, but it's like quadratic on the left side, and then it's just 0. So this is differentiable. This is a point of non-differentiability that prevents us from using gradient-based optimization methods. Can't use gradient descent. You got to use something else similar to what you do with lasso that ends up being slower to converge in terms of the algorithm. So by doing this, you end up getting a much faster algorithm. But you actually change the loss, and the performance, in my experience, is a little bit worse. So, but interestingly enough, that is the default. So if you don't want that to be the default, you got to specifically tell it to use the hinge loss instead of the squared hinge loss. So that's what I'm doing here. Also, not surprisingly, for the multi-class option, you are going to tell it, do you want to do the simple approach or this joint approach? And yeah, by default, it does this. This is simpler, it's faster. So that's the default. In this case, we're going to tell it to do Kromer-Singer because it works a little better. And when we do this and we run this on our MNIST dataset, we get 90.7% accuracy, which is 0.5% better than our logistic regression. Okay, so it's nice to see it doing better, but after all this work, it's a little bit disheartening maybe, right? We did all this derivation, all this stuff, and it's like, all we got is a 0.5%. It's kind of frustrating. So the thing is, though, the story's not over. The big part, the big advantage is something we'll talk about next time, and that will give us a huge leap in performance compared to MLR. But it's going to build on this idea just with one powerful twist. So we'll save that for next time, and I'll see you guys on Wednesday.